start with the second part of the session. And we have something new. We have now a timer that gives at least some sort of advice on how long you should talk. And the first speaker is Kei from Japan, I guess, and she would talk about tsunami generated by the 17th century great earthquake of East Hokkaido in Japan.
Thanks, Mr. Chairman. I'm Kei Ioki. I'm a student of Hokkaido University, Japan. I'm talking about the tsunami generated by 17th century great earthquake of East Hokkaido, Japan. Introduction. I first talk the introduction and talk about the purpose of this study and describe a method of tsunami numerical simulation and talk about the results of tsunami numerical simulation of 17th century great earthquake. Finally, I'll make some conclusions. First, introduction. This is Japan and Kamchatka. These ellipses show many great undersurface earthquakes occurred along Kurilu-Kamchatka subduction zone. In this area, 2003 and 1973 earthquake, the great earthquake occurred. The interval of 300 to 500 years. So I will talk about the earthquake. Focus on this area, the coast of Pacific Ocean, East Hokkaido, many more or marsh and lake can be seen. So many peak layers exist for more than 4,000 years. So many tsunami deposits and volcanic ash can be seen. In eastern Hokkaido, 11 tsunami sandbeds were found for about 4,000 years. So the recurrence interval of tsunami is 300 to 500 years. Because latest tsunami sandbeds was found just below volcanic ash of 66.7 thermal eruption. So it is found that the latest event was 17th century. Tsunami deposit can be seen 1 to 4 kilometers inland from the coast. About 17th century great earthquake, Satake et al. 2008 estimated the fault model of 17th century earthquake. So let rectangle show the end model, length of 200 km and width of 100 km and slip amount equal 5 meters. Blue rectangle shows the T model, so length of 100 km, width of 100 km and slip amount equal 10 meters. In this earthquake, two models slipped together. In Satake's paper, fault model was estimated from comparing observed tsunami deposit and calculated tsunami inundation area at 5 locations. This figure showed at Oikama Nainuma. So many tsunami deposits were observed inland. And the color part shows the computed tsunami flow depth. On the other hand, Hirakawa et al. 2005 found the tsunami deposit at terrace near the coast and estimated the water elevation. This figure shows Cape Elimo to Cape Nosatsu from east coast of Hokkaido. This figure shows the coastal tsunami height of east coast of Hokkaido. Red line shows the calculated tsunami height by Satake's paper. And blue dot shows the measured tsunami height by Hirakawa's paper. So the tsunami height is 10 to 18 meters. Tsunami height of Satake's paper is smaller than tsunami height of Hirakawa's paper. This area. The purpose of this study is to find the fault model of 17th century great earthquake occurred off East Hokkaido that can explain both tsunami inundation area and major tsunami height. About fault model, already tsunami inundation area were estimated using N and T model by Satake paper. So fault model that tsunami height at the coast is only higher are needed. Because of that, fault model that width is short but shallow part of the sea near the clear trench. Third, tsunami numerical simulations. About fault model parameter. So we use the model N and T and added the S model, length of 100 km and width of 50 km. The S model was set near the clear trench. So we assume that three models slip together in this earthquake. The fault model parameter of all model is strike equal 227 degree, dip equal 20 degree, and lake equal 90 degree. About calculation area, tsunami height was calculated at large area, the range of 142 to 149 degree east, 39 to 45 degree north. The tsunami height and tsunami inundation were calculated at shown in black dot, Rekihunegawa, Oikamanai-numa, Yudo-numa, Chofushiko, and Pashikuru-numa. About bathymetry, grid size of 10 arcseconds was used at large area. Around near the area of calculating tsunami inundation, grid size of 1 arcseconds were used. Basically, these topography and bathymetry were used. About tsunami simulations, first, ocean bottom deformation was computed using equations of Okada 1985. Second, ocean bottom deformation was assumed to be equal to ocean surface deformation. Third, tsunami waveforms were computed using ocean surface deformation. In order to compute propagation of tsunami, non-linear long wave equations were solved. Tsunami inundation were solved using nonlinear long-wave equation. So in the case of the linear equation of motion, it consists of acceleration term and pressure gradient. In the case of nonlinear, acceleration term and pressure gradient plus advection term and bottom friction were used. Equation of continuity is written like this. Post result, tsunami inundation area and height was computed using the Ford model. Compared calculated tsunami inundation area and the area that tsunami deposits were found. Compared calculating tsunami height and measured tsunami height. Slip amount equals 30 meters of S model was estimated. The total seismic moment of the earthquake of NTS model was calculated to be 14 multiplied by 10 to the power 21 Newton meter magnitude 8.7 by assuming that the rigidity is 4.0 multiplied by 10 to the power 10 Newton per meter square. A result of computed tsunami inundation at Rekifunegawa. Flow depth is shown this color, and water elevation of Hirakawa's paper is written in black, and water elevation of our result is written in red. Water elevation includes the flow depth and topographic height. Red dot shows where tsunami deposits were found. At Oikama-Nainuma, the water elevation of our result is a little higher than the Hirakawa's paper. At Yudonuma, water elevation of our result and Hirakawa's paper is the same. And computed tsunami inundation area are little small. At the Chofushiko, water elevation of our result is a little higher than Hirakawa's paper. Computed tsunami inundation area is fit to where tsunami deposits were found. At Pashukurunuma, the area tsunami deposits were found is the same the computed tsunami inundation area. This conclusion, we assume the Ford model of 17th century great earthquake occurred off East Hokkaido. Tsunami inundation area and height was computed using the Ford model at 5 locations. Slip amount equals 30 meters. Obvious model best explain the measured tsunami inundation and height where tsunami deposits were found. The total seismic moment of the 17th century great earthquake was calculated to be this amount by assuming that the rigidity is this amount. Thank you very much for attention.
Question?
Yes, you said 8.7 as the magnitude.
Yes.
But can you give some range of the uncertainty? Well, what is the largest reasonable value and smallest reasonable value centered around 8.7?
Already N and T models fault parameter is estimated, and so
간단히 얘기해서 4-4-1, 4-4-1 정도는 알아요.
So we assume slip amount equals 30 meter in the case magnitude 8.7, but maybe 25 meter or 35 meter it's okay. So magnitude 8.7, minimum is magnitude 8.7 and maximum maybe magnitude 8.8.
Finished? Okay. Have you considered the possibility that maybe this could be a different kind of mechanism, like the 1933 Sanriku normal faulting earthquake, which had a much larger aspect ratio of its displacement versus length?
Comparing 1993 Sanriku earthquake,
Yeah.
it's in the cases width is almost same 15 kilometer, but length is a little small.
Well, the 1933 is a snappy earthquake, which has more higher stress loss because it's intraplate. So you can get an aspect ratio which is much more, which is much sharper.
Yeah.
So perhaps this is another model to consider.
Any other question?
Yeah, but my question is pretty close to the one. So, so why did you decide to add this last part in the fold? And what is the effect of this last part that you had in your model to your result? Because you showed a comparison between your result and observations, but what is your model result if you don't add this last part?
Yeah, and in London, in Anderson area can describe no S model, but the height of coast is smaller. The height of coast is small, non-S model. So we added the S model.
15 meters is the observation, or is
Yeah.
without the S model?
No, all these models.
Why don't we follow up with this discussion in the break? I think it takes a long. So let's move to the next speaker.